Hello and welcome to this abbreviated discussion about selecting the best test. In this particular video, I'm going to be talking only about the parametric tests, and I won't be going into the non-parametric versions. And so what I'd like to do is first start out with a lot of the tests that you probably are familiar with that are bivariate analysis. In other words, there are only two variables, one predictor and one outcome. And then after that, I'll show how some of the multivariate, like multiple linear regression and ANOVA, Factorial ANOVA, repeated measures relate to those other ones. They're really just extensions of those. And so let's start out by thinking about the t-tests. First of all, we have something called a one sample t-test, and I'm going to have to abbreviate some of these, so I'll just say t-test, just because I don't have quite the fine ability to draw today. And we also have a paired samples t-test. And I've drawn those in the same color because they really are very much related to each other. Mathematically, behind the scenes, they are pretty close to identical. They both go off of the assumption that we are comparing whatever it is that we measured with something else. In a paired t-test, we happen to compare that to another measurement that was measured at baseline. In a one sample t-test, we compare it to, say, a reference value. I'll just put R here. So that one sample t-test and the paired samples t-test are very similar to each other. Next, we have an independent samples t-test and a one-way ANOVA. And it's called one-way ANOVA because we have only one predictor variable. In other words, we have an outcome variable and we're trying to predict it with just one variable that has several categories. With an independent t-test, we have only two categories, and with a one-way ANOVA, we can have three or more categories. And so these, again, are very similar to each other, and so I've drawn them both in green. And it's just that the only difference is that here with the independent samples t-test, I really only have two categories, so it's a much simpler version of this same mathematical concept that the one-way ANOVA is trying to represent. The third kind of predictor variable that we might be looking at actually comes to us with simple linear regression. And with simple linear regression, we have a continuous predictor. And so if I was to draw what those look like, I would say with an independent samples t-test, here we have our two groups. Let's say maybe we have men and women. We have two different hospitals or two different programs. We have some kind of an outcome variable that's continuous. And when we look at our data points, what we're doing is we're trying to compare, come on, little dots, we're trying to compare the average for those two groups. And if I had very, very good skill, I could draw my little tiny normal curves here. And so we're looking at whether the average for those two groups is the same or whether there is some kind of a difference between those two. With a one-way ANOVA, we're looking at three or more groups. We may have A, B, and C. Again, we have kind of some, maybe obviously more data points than what I'm putting on here, but we're looking for where those the kind of like little normal curves actually come over here to the continuous left hand side of this whatever we're saying is a continuous variable, and we're looking to see if those averages are different between groups 1, 2, and 3. For simple linear regression, on the other hand, what we have here is we have a continuous variable. Oops, those are actually supposed to be separate vertical lines. Right there, more like that. And so we have something on a continuum that is predicting this outcome variable. And so what we end up with there is, instead of discrete groups, like here we have a discrete group, and here we have another discrete group. Instead of having a discrete group, we really have them spread out across a continuum. And so here we have more of a cloud. And then we can draw a line of best fit for that. And so that's really kind of how those are different. With paired samples t-test, if we're looking at this over here, then what we did is we measured something for a particular group in the before. Oops, that's not really helpful. We measured the before variable, and then for each person we measured an after, and within that person, within that paired set of data, we're really looking at whether that changed from the before and after. For a one sample t-test, we just measured the after, and we're comparing that back to some reference value for each person. Now, in reality, these are very simple tests, and in the real world, what ends up happening is we do things that are much more complicated, and so we have to be able to adjust for a lot more things than just having one predictor and one outcome. So, for example, instead of just doing a paired t-test, have you ever heard of a test where we measured something at baseline, and then we measured again at 2 weeks, and then we measured again at 4 weeks, then we measured again at 8 weeks, and then maybe 12 weeks and 24 weeks, and we keep measuring these things over and over and over again. And the paired samples t-test really isn't flexible enough to be able to handle that. And so what we end up with is something called repeated measures ANOVA. And that's where you can make this measurement at baseline. You can measure it again at time 1, you can measure it again at time 2, and on and on. And so you can just keep making those measurements, and repeated measures ANOVA then makes adjustments for the fact that we're keeping on measuring that thing over and over again. So what I like to think of is my one sample t-test is the simplest version of this kind of test, where really I'm looking at, I only measure something one time. Here's my one measurement. With a paired t-test, then I not only measured it that one time, but I measured it at baseline so that I can compare each person to their own personal baseline rather than just a reference value. And then with repeated measures ANOVA, that gives me the flexibility really to be able to measure over and over again. I can measure it not only just at one time and compare to baseline, but I can measure it time 1 and time 2, and each one of those can be compared to the baseline. Each one can be compared to the previous one. Like if you think of a weight loss program or some kind of a hypertension intervention, we want to know over time what happens, not just at the very beginning compared to the very end. So that's where repeated measures ANOVA fits into the grand scheme of things. After that, I like to draw this imaginary line between these, because what we're doing over here on the left-hand side is really quite different mathematically than what we end up doing on the right-hand side. So over here on the right-hand side, we can extend this idea of the one-way ANOVA to something called factorial ANOVA. You'll have to use your imagination a little bit with that. But basically what factorial ANOVA does is it is an extension of one-way ANOVA, just like repeated measures ANOVA was an extension of a paired samples t-test. So here we have factorial ANOVA. basically what Factorial ANOVA does, it's also called N-way ANOVA. So in other words, you could have a 2-way ANOVA or a 3-way ANOVA or a 20-way ANOVA or a 100-way ANOVA if you had enough data points. But what Factorial ANOVA does is it allows you to put more than one categorical predictor in order to predict that outcome variable. Remember how here we were putting categorical predictors. So here we have one categorical predictor. It could be 3 different programs or 3 different hospitals or 3 different schools, that kind of thing. And we're looking at whatever this continuous outcome variable. So instead of only being able to put one categorical variable into the model, we can put 2 or 3 or a bunch, and that's dependent on what we put here for the n. If we have 5 categorical variables, we call that a 5-way ANOVA. And so that's what Factorial ANOVA is, because these categorical variables that have 2 or 3 or 4 categories, those are called factors. And so that's where the factorial comes in. So Factorial ANOVA really is an extension of either independent or one-way ANOVA. And remember, this is super duper important. These are really the same test, just dressed up in a different name. So Factorial ANOVA can be an extension of either one. You can have factors or these categorical variables that have 2 categories. You can have factors that have 3 or more categories, and you can mix and match those. So you could put both gender and hospitals into this Factorial ANOVA. As long as all of your predictor variables are categorical, we call that Factorial ANOVA. So that's where the Factorial ANOVA comes in. The next kind of test that we can use that has more than one predictor variable is called multiple linear regression. And we basically take our simple linear regression and we can add more variables and call it multiple. And so in our very basic example, we had only one continuous variable as a predictor. In multiple linear regression, we can put 2 continuous variables or 3 or 10 or however many we want. Now, the other thing to remember about multiple linear regression is that it is what I call the grandfather of all of these. And so, really technically, all of these tests are mathematically behind the scenes really the same thing. And so, technically, I could run a one-way ANOVA as if it's a multiple linear regression. I could run a Factorial ANOVA as if it's a multiple linear regression. I could run independent t-test or a paired t-test. It's just how do I package those variables and plug them into that multiple linear regression equation? If you knew exactly how to put those in, then you can run them all the same. The reason that we split them out is that they have different assumptions and different problems. And so the kinds of things that I need to address with a paired samples t-test are different than the assumptions and the kinds of things I have to address with these other ones. And so we give them other names, but technically behind the scenes, they really are all linear regressions, just dressed up in a different name. So, if somebody asks you, what's the best test? You would actually say a paired t-test. But mathematically, what you are kind of running is a linear regression of sorts. So, if all else failing, multiple linear regression will really do an awful lot of things, but it's only really the right answer to the way to analyze it if those other ones aren't available. Now there's one more test that ends up being somewhat of a combination, and that is called the ANOVA. And this ends up being a combination of factorial ANOVA and multiple linear regression. And let me explain. With ANOVA, you generally are doing some kind of an ANOVA that's like a factorial ANOVA, except that you have something called a covariate. And a covariate is a continuous variable. And so we're running an ANOVA, but then we realize that we need to correct for something that is not categorical or not factorial. And so what we end up doing is taking this factorial ANOVA and turning it into more of what would be considered a multiple linear regression so that we can do this ANOVA. So remember how I said really they're all the same test dressed up in a different name? This too is really just a multiple linear regression, but it has its own special issues, its special assumptions, the things that we have to check for and possibly adjust, and so it's called ANOVA. And so I might have one or more of these categorical predictor variables. Maybe I want to tell the difference between 3 hospitals or 3 schools or 5 states or 10 different programs, and I want to be able to look and see if the averages of those 3 or 5 or 10 programs are the same. I'm doing something like this. But then I realize that I need to adjust for a continuous variable. And in order to adjust for that continuous variable now, instead of doing a factorial ANOVA, I have to do what's called an ANOVA, because that continuous variable is a covariate. Categorical predictors are factors. Continuous predictor variables are covariates. So that's why we call it an ANOVA, because it's an ANOVA with a continuous adjuster. So that is, in a nutshell, a bunch of different statistical tests that you may need to be able to choose between, and hopefully that helps you to be able to pick the best one for your particular testing scenario.